Let's start application of matrix and determinant, and next we have properties of inverse of matrices. Theorem 1.4. What it says you have to remember here. If A is non-singular matrix. What is non-singular matrix? Non-singular matrix means, as I already told you, determinant of A should not equal to 0. Determinant of A should not equal to 0. That is, the things is nothing but non-singular. The next one, first what we have, first theorem 1.4 first point is determinant of A inverse. Determinant of A inverse equals to 1 by determinant A. As already we know that A inverse is nothing but 1 by determinant A only. The same thing here arguing determinant A inverse is nothing but 1 by determinant of A. Next, second one, what is that? A transpose of whole inverse. A transpose of whole inverse. A transpose of whole inverse is nothing but A equal to A inverse of transpose. That means transpose inverse we can exchange here. Here first you take transpose, then you need to take inverse. Whereas here inverse you take first and then transpose next. Then in both the situations the value will give the same. Okay. Next one, let's come to this one. Lambda A whole inverse. Actually this should be lambda A whole one. This is not here, it should come whole inverse. Lambda A whole inverse. Lambda A whole inverse is nothing but 1 by lambda A whole A inverse. That is, lambda, if you apply inverse now, it will become 1 by lambda A, and then A inverse is for A we can take. That is the thing they are saying in this theorem. As you can, one more time you can see here, theorem 1.4 what it's saying now. If A is a non-singular, why it's non-singular now? Determinant A value should not equal to 0. That is, determinant A value should not equal to 0. Which means here you can see 1 by determinant A is there. Determinant A if becomes 0 now. That is, this equals to 1 by 0 means it will turns to infinite. This should not equal to what? This value should not turns to 0. That's the thing they are saying here. Okay. Next one, A transpose whole inverse, we can write it as A inverse whole transpose. Then here lambda A whole inverse is equals to 1 by lambda A into A inverse. This is the theorem 1.4 is saying. Let's see next one. Left cancellation law. Next theorem is left cancellation law. Next theorem, left cancel. Why they are saying left cancellation law? You just see how the statements are. Let A, B, C be a square matrix of order n. You can note here all the results, all the property is only for square matrix. It should not be a non-square matrix. It should be a square matrix. So here they are saying let A, B, C be a square matrix of order n. Okay, and if A is a non-singular, non-singular means determinant A value should not equal to 0. Determinant A value should not equals to 0. Then AB equal to AC, AB equal to AC, AB equal to AC. If it is this things is there, then you can cancel. Then we have B equal to A. That is, this straight away it's coming B equals to A. You can see here A, this A and this A is going to cancel. So we get the same result, B equal to C. This is B equal to C we will get, because it get cancelled. AB equal to AC now. A get cancelled, then we have B equal to C, B equal to C we are getting. So I have before I have written A equal to B equal to A, that's wrong. B equal to C we need to write. Once again we will see why it's left cancellation it's coming now. The A's are left to the terms. AB is there, for B A is a left. AC is there, A is a left. It should not like this. AB equals to, for example, CA. Now we can't cancel like this, because one is left is there, another is right is there. So this mixed thing should not be there. Is that clear? So once again I repeat this one, what they are saying now. Let ABC be a square matrix of order n. If A is a non-singular, that is determinant A value should not equal to 0. And AB equal to AC, then B equal to C, which means A, both A are on left side. So we can easily cancel, so we will get it as BC. So this is one of the important result. This is one time, these are all 5 mark questions. Now we will see the result, how it is there in the while we are school is reopening. Let me go to next theorem. Next we have right cancellation law. As you earlier have shown left cancellation law, here you are going to see right cancellation law. Let, here what is that? Let A, B, C be square matrix of order n. Same thing. If A is a non-singular, then BA equal to CA, then BC, B equal to C they are saying. Which here you can see here. Here it is BA equal to CA is there. BA equal to CA. Here you can see A is on right side of B and here A is on right side of C. So here we can cancel A cancel now, B equal to C, B equal to C. So that's the thing we have in this case. So what the right cancellation law means, A's are in right side. So that is the theorem. Next we have. So first we have shown let A, B, C be a square matrix of order n. And if A is a non-singular matrix, then BA equal to CA. These are all thing is called necessary. Up to this is necessary. Up to this is necessary. Then this is nothing but our result. If it is BA equal to CA, both A on right side, so that we can cancel and then we can write B equal to CA. This is nothing but right cancellation law. Okay, next we will go to next theorem, that is we are having reversal law for inverse. Next we are having reversal law. What is the reverse means? You know that one, ulta, reverse we need to write. Here statement is like that. If A and B are non-singular matrix, if A and B are non-singular matrix of the same order, that means A is 3 cross 3 now, B is also 3 cross 3. If A is 2 cross 2 now, then B is also 2 cross 2. It should not like that A is 2 by 2 and B is 3 by 3. These are all not, though they are square matrix, but order is not same. That's why they are insisting the order should be same. Is that clear? If A and B are a non-singular matrix of same order, then the product AB, product means multiplication. If you multiply both the matrix AB, then the product AB is also non-singular. First of all, A and B should be non-singular. That is, individually you are taking a determinant value. The answer should not comes to 0. After multiplying A and B, that determinant if you take, that is also what should come? Non-singular. That is, determinant value of AB should not equal to 0. Then you need to apply this one. That is, AB whole inverse equals to, first will come B inverse, then A inverse. You can see here, first AB is there. Here reverse they have written BA. Is that clear? Here combined inverse is there. Here individual inverse is there. That's why we call it as reversal law, because AB is here multiplying and the next side we can see BA is the reverse. That's why we name it as a reversal law for inverse. This is theorem 1.7. Once again I read the statement what they are saying. If A and B are non-singular matrix of the same order should be same, then the product AB is also non-singular. Then we can write AB whole inverse, we can write it as B inverse, A inverse. That is the theorem 1.7. Next law is the law of double inverse. Law of double inverse. Next law is what we are having, law of double inverse. What they are saying in the law of double inverse means, if A is a non-singular, as you know determinant value should not equal to 0, then A inverse is also non-singular. Here both the things, A as well as A inverse, both should be non-singular, which means that determinant value of A, should not equal to 0 and determinant value of A inverse should not equal to 0. Such thing is happening. Then if you take A inverse of inverse, A inverse of inverse if you are taking now, that value is equals to what it's coming? A. That value it's equal to, it's coming here as a we can say. This is nothing but law of double inverse. As you know that law of double means 2 times inverse is there. One is inside the bracket, another one outside the bracket. I repeat this statement. If A is a non-singular, then A inverse is also a non-singular. and A inverse of inverse equals to A is there. That is the law of doubling. Okay, now come to the next theorem, theorem 1.9. It's very important theorem. Why it's very important theorem? Now, based on this one, we have so many formulas we are going to in this theorem, and then we need to apply this results and theorem in our problems. So let's we see one by one. Some 4 or 5 problems, 6 is there. Let's we see one by one. If A is a non-singular square matrix of order n, here 3 things are there. Given matrix A, 3 things is there. Given matrix A should be a non-singular, which means determinant A equal to not equal to 0. Next one, it should be a square matrix of order n. Square matrix of order n like 2 by 2, 3 by 3. Here what should become n by n. Since theorem is generally general statement, so that's why they won't say second order, third order. They say in general it's order n. That's the thing. It should be non-singular, it should be square, and it for the n times, order n times they are saying. The first subdivision what they are saying, adjoint A of whole inverse. Adjoint A of whole inverse. We can write adj of A inverse. We can write adj of A inverse. Once again you see, adjoint of A inverse. Adjoint of A whole inverse. We can write adj of A inverse, which is equal to 1 by determinant A into A. 1 by determinant A into A. That is the first subdivision. As you know how to find adjoint A and then how to find A inverse, it's very important results. Please remember this results. It's very useful for 1 mark purpose, so be careful. Okay, it will be confuse you because adj is there, so inverse is there, so don't get confused on it. 2 to 3 times you write, you can easily understand that one. That is, here you need to take first you need to take adjoint for a matrix A. After that one you need to find its inverse. Whereas here is, first you find inverse. For that inverse value what you get, that you have to, for that matrix you need to take adjoint. Is that clear? Here you take first adjoint, then you apply inverse. Here you find first inverse, then you apply the adjoint rule. After that one, these 2 values will be equal to 1 by determinant of A into A, they are saying. So that's an interesting point. Second theorem, you can see here, it's very important. So many times they're asking in 1 mark as well as problem is also is there. Determinant of adjoint A equals to determinant of A whole power n minus 1. Determinant of A whole power n minus 1. That is, determinant of adjoint A is equal to determinant A of whole power n minus 1. They are saying it's very important results. How it's coming? While the school reopening, I will explain you how we are going to see. Next you can see adjoint of adjoint A. Adjoint of adjoint A equals to determinant A of n minus 2 into A. Determinant A power n minus 2 into A. Into A means you know that it's multiplication. A is an ordinary matrix. Here determinant A value will give numerical, and then you need to raise its power to n minus 2. Like it will come 2, 4, 3, like number will come. That number you need to multiply with the matrix A you need to do. It's very important. You are going to take adjoint of adjoint A. Adjoint of adjoint A, which is equals to determinant A the power n minus 2 into A. These are also very important. Result we are having, that is third division. Next we have fourth one. What they are saying, you see, fourth one, adjoint of lambda A. Lambda is a non-zero scalar. Lambda is a non-zero scalar. Scalar means number. That number we can say 0 should not be there. If 0 is there, everything you multiply with the 0, the answer will become 0. So that's why adjoint of lambda into A equals to lambda power n minus 1. Lambda power n minus 1 adjoint A. You may ask the question, from where it's come this n. Here also n we have used. Here also n we have no. Here you have order is what? Order is n. That's why it's applying the result. If order is n here, that's why here also n it's coming, here also n it's coming, in here also n it's coming. If order is 3 now, everywhere in place of n what you are going to write now, 3 you are going to write. That you keep it in mind. Here the result what they are saying, adjoint of lambda a equals to lambda power n minus 1 into adjoint a. Lambda power n minus 1 into adjoint a, we can write it. Next result we are having adjoint of adjoint a, determinant of adjoint of adjoint a, determinant of adjoint of adjoint a, which is equals to determinant a the power n minus 1 square. Determinant of adjoint a value is how we are writing, equals to determinant a to the power n minus 1 square. Here 2 power is that, so be careful, power of power is that. Determinant a whose power is n minus 1, that power is square is that. That's it, 2 things is that. Be careful here. Determinant of adjoint a equals to determinant a the power n minus 1 square we have. And finally 6th result we are having adjoint a transpose. Adjoint a transpose we can write it as adj of a transpose. As you know, for this matrix A, first you need to take adjoint and then after that one you take transpose for that one. Whereas in this case, first you take a transpose to the given matrix, after that one you take a adjoint for this one. And then generally we can see one more time, one notes is there, you can see here. Before going to notes, once again you see the result itself, it's very important. Theorem what they are saying, if A is a non-singular means determinant A value should not equal to 0, of order should be what, n. Then we have 6 results. What are the 6 results we are having? 6, one by one you see. Adjoint of A inverse equal to adj of A inverse we can see, or we can say 1 by determinant A into A we can say. Here we are having determinant of adjoint A we can write as determinant of A n minus 1 we can write. The third result, adjoint of adjoint A equal to what we can write, determinant A power n minus 2 into A we can write. Then fourth result, adjoint of lambda A, adjoint of lambda A, we can write it as lambda power n minus 1 into adjoint A, where lambda is a non-zero scalar. Non-zero scalar na, it's a number, that number should not be 0, except 0 anything number will be there. Then fifth one, what is there, adjoint of adjoint A, which is nothing but determinant A into n minus 1 whole square. And adjoint of adjoint A is determinant A into n minus 1 whole square we are having. And the next one, sixth one, adjoint of A whole transpose is nothing but adjoint A whole transpose. First you need to take adjoint for a given matrix, after that one you take a transpose to that one. Here you take a transpose to the matrix first, after that one you take a adjoint. Now one more important result is there here, you can see note we are having this one. A is a non-singular matrix of order 3. A is a non-singular matrix of order. Special case, order in theorem we have order n, whereas here we are having order 3 we can say. Order 3 means in place of n we are going to write as a 3. We know the result is what, adjoint, determinant of adjoint A is nothing but determinant A power n. Just now we have shown this second one, so that you can see here. Okay, that the result only I have written. Adjoint of determinant of adjoint A equal to determinant A power n minus 1. Since order is 3 here, so in place of n we are going to write 3. So 3 minus 1 we are getting 2. So adjoint A equals to what we are writing, determinant A square is done. If square is shifting to that side, it will become square root. As you know, square root while you are putting, you need to write plus or minus 1. So determinant A value how we can write now, plus or minus square root of adjoint A. I repeat, determinant A value how you are going to write, plus or minus square root of adjoint A you can write it. This is not wicked, we know that. This again, A inverse equal to formula, A inverse formula, last class we have taken. A inverse equal to 1 by determinant A into adjoint A. 1 by determinant A into adjoint A. So A inverse as such, just now we found the determinant A value. A determinant A value is what? Plus or minus square root of adjoint A. This value I am replacing here. So here we are getting 1 by plus or minus square root of adjoint A into adj A. This way, if adjoint is given, you can easily find inverse. If the matrix A is also is not given now, you can easily find A inverse for the given matrix. I think it's very important theorem regarding matrix 1.9. Based on this one, we are going to see a few problems on it. Let's we see those things now, but it's very important, keep it in mind. Next we will see example 1.4. It's problem, but actually it's not a problem like theorem they have given, but it's a problem. Here what is the problem is saying, if A is a non-singular matrix of odd order. Odd means what? That is number, it's not a divisible by 2, or we can't write a number, it's a multiples of 2. That is, odd is nothing but simply we can say 1, 3, 5, 7, like that number. Okay, so if A is a non-singular matrix of odd order, so odd order means like 3 cross 3. We won't say 2 cross 2. 2 cross 2 is a even. Odd means 3 cross 3. Then 4 cross 4 won't come. 4 cross 4 is even. Then 5 cross 5 will come. So here order will odd means. So what are the order will come for a matrix? Now 3 cross 3, 5 cross 5, 7 cross 7, like that will come. If it is A is a non-singular matrix of odd order, prove that determinant of adjoint A. Prove that determinant of adjoint A. Prove that the determinant of adjoint A is positive. Determinant of A is a positive. That is the thing we need to write here. We need to prove here. So let's go. This is the solution I already have written here. You just see how I am going to explain this one. First you need to understand odd order means what? Either it should come 1 by 1, 1 cross 1, 3 cross 3, 5 cross 5. Since this is square matrix, we can write as simply number 1, 3, 5, 7. Means you have to understand it is what? 1 by 1, 3 by 3, 5 by 5, 7 by 7. Likewise, you need to understand. In general, odd number means 2m plus 1 we can write, where m belongs to z. Why m belongs to z means here m is 2m plus 1. Z means what? Integer. You know that integer means 0, 1, minus 1, 2, minus 2. Likewise will come. For example, you give 1 here, 2 ones are 2, 2 plus 1, 3 will come. So, if I am giving m as a 1 now, 2 into 1 plus 1, answer what will come? That is 2 plus 1, that is we are getting 3. So 3 is what we are getting odd. This is the general format of odd number. This is a general format of odd number. 2m plus 1 is what? General format of odd number. Instead of saying 1, 3, 5, 7, it's an infinite number series will be generated. That's why we are writing in general it is what? 2m plus 1. Okay, as we know by theorem, just now we have some theorem. In that theorem we have results, that is adjoint. This result we are having, that is adjoint of A. Determinant of adjoint of A we can write as determinant A whole power n minus 1. Determinant of adjoint A is nothing but determinant A whole power n minus 1. Here order is what they are saying, odd order they have given. Odd means 2m plus 1. In place of n, I am writing here 2m plus 1. This is minus 1 is formula minus. So plus 1 minus 1 get cancelled now. Determinant A power is what? 2m. The power 2m is nothing but even. Since already we have saying that m is what we are saying. M is z. Z is nothing but integer. For example, 2m means m you put 1. 2 ones are 2 will come. If I am putting 2 here, what will come? 2 2s are 4. I am putting 3 here, 2 3s are what will come? 6. You can see here, either I am putting 1, 2, 3. 1, 3 are odd. And then if we put odd number also, answer we are getting 2 and 6. That is nothing but even. Anything the power is even now, definitely there is no chance that it will come negative. There is no chance that it will come as a negative. Why? If power 2 means, for example, minus 1 into minus 1, what will become? Plus 1. So that's it enough. 4 times, 6 times, whatever may be the power, the answer you are going to get only what? Positive. That is the proof for this result. Always positive. Hence the proof. Is that clear? Let's see one problem. It's very important problem. It's from a question we can say. What they are asking, find a matrix A. We need to find a matrix A. If adjoint A, so adjoint A is given, you need to find matrix A. What's adjoint A? So adjoint A equal to 7, 7 minus 7, minus 1, 11, 7, 11, 5, 7. That's a question we are having. I repeat the question. Find a matrix A. If adjoint A equal to what is that? 7, 7 minus 7, minus 1, 11, 7, 11, 5, 7 is there. Okay, now it comes to the solution. What's the solution? How we are going to find now? Again theorem 1.9 only, the result we have shown. Determine A, how we can write? Plus or minus 1 by root of adjoint A, adjoint of adjoint A. That is the result we are going to find here. Okay, so this is this using the theorem 1.9 we are getting. So use this one, we need to find. Already they have given adjoint A matrix, so we need to find, for this adjoint matrix I need to find one more adjoint. After that finding adjoint, we need to square root the adjoint A, that is determinant value of adjoint A. Here we are going to find determinant value of adjoint A. For that one we need to find its square. Let's we go to the problem. So what the problem is saying, you just have a look. We need to find determinant A for adjoint matrix. So I have written 7, 7, minus 7, minus 1, 11, 7, 11, 5, 7. So now we need to find determinant value. I have already found that this one. You can see here one by one. See, first thing I am expanding to first row, this row. So this row, this column deleted. As you know, 11 7s are 77. Formula minus 5 7s are 35. So 7 into 11 7s are 77. 5 7 5s are 35. So 77 minus 35 it's coming. This position is negative, that's why minus 7. So this row, this column delete now. Minus 1 into 7 is minus 7. Formula minus 11 7s are 77. So minus 7 minus 77. This is minus 7 I have written. Then this row, this column deleted now. Minus 1 into 5 minus 5. 11 11s are minus 21. That's the thing. If you simplify everything, you will get the answer is 1764. 1764. That is the value for adjoint A, determinant A value. Now I am finding square root for this one adjoint A. Square root of 1764 if you are doing means we are getting what? 42. Since we are taking square root, the value should be in plus or minus. That I have taken. So square root, one value in the formula we have found out. That is determinant A value, square root of determinant A value, we have got it as 42. Next you need to find adjoint of adjoint A. So adjoint is here, don't worry about it, because this adjoint they are already given in the question. So that's why I have written adjoint A value, this matrix I have written here. Again, how will you find adjoint? Simple. You have to find minor and take a transpose and cofactor. If you are doing transpose minor, how will you going to find? For example, for 7 minor you want to find now this row, this column deleted, cross multiply and get the value and write it. Then this minor, how will you get? This row, this column deleted, cross multiply and then we'll get a minor, write it, and position you need to write it here. So already we have taken inverse. I think I need not want to waste your time, that's why I have written directly this matrix I have written, that is the adjoint of adjoint A. Okay, straight away I have taken the value. After this one, that up to this one is adjoint of adjoint A. This is the value for adjoint of adjoint A. Okay, next the formula is what they are saying, A equals to plus or minus 1 by root of, you can put determinant for understanding purpose, put it square root of adjoint A, adjoint of adjoint A. Square root of adjoint A already we have found 42, that's why I have written 42. And adjoint A matrix, adjoint of adjoint A matrix I have taken here, so that I have written. Now 42 you have to divide it, you will get the A value as plus or minus 1 minus 2 3, 2 3 minus 1 minus 3 1 2. That is 42 42 get cancelled now 1. 84 42 divided not 2 times. 126 42 divided not 3 times. Same number is there, so that's why it's coming. Only the sign is are going to be changes. Be careful regarding that one. This is an important 5 mark question we can say. Okay, next we will see one more problem. Let's see. Okay, you can see here one more problem, that is what they are saying here. Example 1.6, if adjoint A equal to minus 1 2 2 and 1 2 2 2 2 1 is there. Here you need to find what? A inverse. What we have done in the last problem, the same thing, you do it as a homework. Okay, I have given in a homework sheet also, you just see this too. The next question 1.7, what is there? It's like a theorem is there. If A is a symmetric matrix, prove that adj A is also symmetric. Adj A is also symmetric. If A is a symmetric matrix means prove that adjoint A is also symmetric. First you need to understand what is a symmetric. First you need to understand what is a symmetric. Symmetric means if you take a transpose, as you know everyone how to take transpose. If you take a transpose, that is changing row into column, or we can say column into row. If you exchange this row into column, column into row is nothing but what we can say, it's a symmetric matrix. If you are doing that one, then we will say it's a symmetric matrix. I will give one example. You can see here. For example, A I am writing as like this one here. I am writing 1, 2, 3. Here I am writing 4. Here I am writing 2. Here I am writing some 5 here. So here I am getting 6. So 3 now. Here will come 3. Here 5 I am writing. This is a matrix we am having. So for this matrix, if you take a transpose, that is here 1, 2, 3 is there. I am writing that one as a row, as a here column 1, 2, 3. Then next we have 2, 4, 5. That I am writing here 2, 4, 5 I am writing. Next we am having 3, 5, 6. So I am writing 3, 5, 6. I have exchanged this one as row and this I have written column. I have taken row, I have written in column. Likewise I have written. Now you can see what is the difference is that 1, 2, 3, 1, 2, 3. 2, 4, 5, 2, 4, 5. 3, 5, 6, 3, 5, 6. After taking transpose also there is no change. So therefore A equals to what it's coming? A transpose. Which mean that what? They are same after taking transpose. Such matrix is nothing but what we are saying is a symmetric matrix. Here the question is, if A is a symmetric matrix means, then we need to prove J is also what? Symmetric. Let's see the proof how they have given. So I already have told you symmetric means what? A equal to A transpose. That is the thing we have shown in the last example I have given. We know that now theorem 1.96 to position what they are saying, adjoint of A transpose we can write as adjoint of A transpose. Adjoint of A transpose, how we can write now? Adjoint A whole transpose we can write. As you know that A transpose is nothing but how we can write A. So this value A transpose we can write it as A now. This will become adj. Here what is coming? Adj of transpose. Here A equal to A transpose. Likewise in place of A what is there? Adj equal to adj transpose is there. So we can say it is also symmetric. Is that clear what I am trying to say? If A is a symmetric, prove that adjoint is also symmetric. A is symmetric means after changing A equal to A transpose, then also the value is not going to be changed. Such matrix you called as a symmetric. The same thing we have proved here. And finally this theorem we will see what the theorem 1.10 is saying. If A and B are non-singular matrix of order n, again here A and B are a non-singular means determinant of A value should not equal to 0 and determinant B value should not equal to 0. If it is such thing is there now, then adjoint of AB equals to HB or J. Adjoint of B into adjoint A. As we have shown in reversal law, that is AB whole inverse equal to B inverse A inverse we have shown now. Similarly here for adjoint we are doing. Adjoint of AB we can write adj B first and then next we are having adj A. In this way we can do this theorem. This is also important theorem. Okay, this is the last thing. It's homework I have given here. You can see I will take a photo and I will send you photo also. Here two things is that example 1.8, this already I have told you example 1.6. 1.8 is verify the property, that is A transpose whole inverse equal to A inverse whole transpose. Here its number is given 2 by 2 matrix 2917 is there. Okay, first you take a transpose for LHS, this problem LHS. First you take a transpose, for the transpose you find inverse. Is that clear? That what's the formula? A inverse equal to 1 by determinant A into adjoint A. That's a formula you can use. For RHS, first you take a inverse, then you take a transpose. After getting separately, LHS separate, RHS separate, check whether it's what their value it's coming equal or not, you check it. The next we have example 1.9. What the example 1.9 is saying now, we need to verify AB whole inverse equal to B inverse A inverse. That is we are saying already just now we have shown adjoint. Similarly here AB whole inverse equal to B inverse A inverse. Here LHS is AB whole inverse. First you multiply A and B. After multiplying A and B, what the result will come? that result inverse you find it. For that result you need to find inverse. Okay, after that is one result, you keep it in mind. Next one, to do RHS, for B find B inverse, for A find A inverse. After getting B inverse and A inverse, multiply B into A. Don't exchange the order is very important here. Don't multiply A inverse into B, anyway it's same. In matrix it's not same. So first you put B inverse matrix, then you put A inverse matrix, and 7 method you applied, 7 structure you applied, and you get the result. And then last, very important, remember all results and theorem I have said, so that's very important. Okay, yeah, problem you can practice, you will get the results only. Now you learn, now in future it will useful. First you remember the result, then it will be easy to you. I think this video I have discussed a lot of theorems and results. I hope it's going to be useful to you. Make use of it. Thank you.